everyone, I'm Olivia Pratama with Oscar Linares and Christopher Lopez. We are part of the Electromechanical Systems Engineering Technology, and our project is called the Mighty Mouse, advised by Dr. Boscovich.
Hello, everybody. My name is Christopher Lopez. The motivation behind our project was to design a wireless optical mouse that utilized kinetic energy in order to charge a small storage battery. Our goal behind our project was to reduce the impact that battery has on our environment. In order to do this, we wanted to increase the overall lifespan of a battery, which will increase the overall lifespan of an electronic device, reducing the overall amount of e-waste that ends up in landfills. When it comes to electronic devices, we live in a throwaway culture where when something stops working, it is easier and usually cheaper to just throw it away and go out and buy a new one. However, electronic waste consists of toxic chemicals, most mainly heavy metals and acids, along with non-degradable plastics. Our goal with this project was also to highlight the process of engineering development and design methods that we have learned throughout our college career here at Cal Poly Pomona. Next slide, please.
For our project objective, our primary objective is to combine electrical and mechanical components into a wireless optical mouse. We wanted to use a simple gear system and common low-cost components while also taking the environment into consideration. Our aim is to lengthen the usable life of a lithium button cell battery and replace alkaline and LiPo batteries in order to reduce our overall carbon footprint when producing mice.
In order to begin our project, we first needed to determine our design requirements. For the mechanical aspect of the mouse, we wanted it to be ergonomically feasible, meaning we wanted it to fit comfortably in the palm of your hand while maintaining a similar size, weight, and feel to that of a regular mouse. After reverse engineering a computer mouse, we found that the electronic components require a minimum of 3 volts and a max of 3.7 volts with a current load of 0.2 milliamps. Some requirements that we set for the mouse ourselves was that we wanted it to have a battery level indicator and last a minimum of 1 hour. Next slide, please.
Our approach on the project is to create an electric generator that is sufficient enough to give voltage and current in order to support a mouse by using a human power generator. This requires integrating a generator and drivetrain into a mouse while also creating an ergonomic housing similar to other common mice. We also want our device to last longer than a battery's charging time.
So the 3 power generations that we considered were piezoelectric generators, stepper motors, and AC motors. Piezoelectric generators were an extremely good candidate because we found research that claimed that these could produce anywhere from 3 to 7 volts, depending on the force applied and the diameter of the disc. However, while conducting our own test, we could get nowhere near 3 to 7 volts. We tried piezos with various diameters as well as cantilever piezo generators, but we could still not recreate anywhere near 3 to 7 volts, which was required to charge the battery. We quickly scrapped stepper motors because they were so small we couldn't find gears small enough to even be able to test them. That's when we finally decided to go with an AC motor. The reason we decided to go with an AC motor was because it could produce a constant 3.7 volts, which was more than enough to charge our battery. So we finally settled on a micro 3-phase brushless AC generator. Next slide.
So for our battery storage devices, we wanted to test each storage device based on its size, weight, and capacity. We initially considered multiple types of devices. However, after some testing, we quickly realized we would not be able to charge larger capacity devices. After that, we discovered some supercapacitors, which allow for quick charging, but are very difficult to manage their discharging, and also had extremely small capacities. We soon decided on lithium-ion batteries for their weight, ease of charge, and size. Primarily, their ease of charge is what we were looking at because they had a smaller capacity and are easier to charge because of that. And For our mechanical design, we decided to use our AC motor. And when we tested our AC motor, we tested our outputs at different speeds and were able to generate an output of 1.4 volts at approximately 200 rotations per minute. With our required output of 3.7 volts, we assumed a linear relationship between rotational speed and voltage, which we then calculated a required speed of approximately 500 RPM to reach our goal. Once we had our desired RPM, we proceeded to consider driving our system with either belts or gears. However, with size considered, we decided to utilize gears since belts had to be custom sized. And also, just to go through the gear train, we have our handle that has 10 teeth to it, the gear that it touches, which is a smaller gear there in the middle, which is 12 teeth, the larger gear, which is 80 teeth, and the final pinion, which is 12 teeth, and that drives our actual generator with a one-way gear. Then that in total gives us a compound gear ratio of 5.56 to 1.
Okay, so key components that we used to build our gear train were a one-way gear, which we 3D printed to fit our AC motor, a handle, and a gear and pinion. So when it's time to charge a battery, the user presses on the handle, which turns the gear and pinion, which then engages the one-way gear, turning the generator. Next slide.
There were many challenges going through the design since we want everything to fit and size still as small as other mices. As you can see here is the top and bottom dimensions of the mouse. It is currently 32 by 129 by 68 measured in millimeters. Optical and gear alignments were the most difficult part of the process because 3D printers were not able to print the exact same dimensions as in SolidWorks. Even when we successfully assemble and spin the gears in SolidWorks, we were not able to do the same in real life. So we had to go through some trial and error to get some stuff to work out. The placements for USB storage, power status, switches are placed around the generator to prevent being in the way of the crank.
In order to build our generator, we use the following components: an AC motor, a full bridge rectifier in order to convert AC current to DC current, a diode to prevent the current from flowing back, a button cell battery to store the energy, and all this was connected to the mouse PCB board. We also added a momentary switch and a battery LED indicator into the circuit. Whenever it was time for the user to look at the battery, he would press on a momentary switch, which would then turn on the LCD display, showing the level of the battery.
The mouse PCB holds a KA8UL mouse sensor, a 50 ohm resistor, a 10 microfarad capacitor, a red LED, and 3 primary mouse buttons. The low-cost optical mouse sensor that we use detects movement and image processing, but relies on a separate lens. The lens used to support the sensor is a 45-degree round plastic lens to help project a red LED for the sensor to read. Our project was designed by using the SOLIDWORKS 2020-2021. It is sliced using the Ultimaker Cura and printed with an Ender 3 Pro. The total manufacturing time for all parts combined is about 8 hours.
For testing and results, we tested our charging system by draining our battery via a blue LED, and the current draw of the blue LED was approximately 20 milliamps. The battery voltage begins at 3.7 volts and is charged 5 times via the generator at minute 1, 5, and 10, which you can see on the right side of our graph. When the battery is assisted, we can see that it ends the 15 minutes of use with a higher voltage than when it is not assisted. And
So this here is a video of Olivia demonstrating how to use a mouse. So we have a lever which unlocks the crank. She cranks in order to charge the battery. And there's a momentary switch to see the level of the battery.
For the future implementation, we would like to integrate all electronics into a single PCB, and we would also like to create custom PC-based drivers that allow the user to view the battery percentage, which would in turn replace the battery level indicator and decrease the overall size of our mouse. We would also like to improve the ergonomic comfort by giving the housing a more refined shape, something a little bit smoother and something that palms a little bit better as well. We would also like to modify the gear train mounting system since it does need some improvement as well since the gears do not seem to mesh 100% of the time. And lastly, we would like to try to find a generator with a higher efficiency and possibly a smaller size. That way we could also reduce the size of the mouse even more.
To conclude our project presentation, we were able to create a hand crank power charging system for rechargeable batteries that will help prolong the usage and reduce the impact of disposable batteries on the environment. Thank you.
Thank you.